welcome to the lecture on remote sensing. So this is the first lecture in the paper remote sensing. In the first lecture I would like to demonstrate about a very small brief about what is the remote sensing, along with when it was started, tracing the history by using aerial photography, and what is photogrammetry explains about. So this lecture remote sensing, as we know that this branch is emerging branch since 1990. Of course, it was started very long back in the year 1970, but from 1990, the development and its application of this technology increases double the time every year, and the demand is also more with respect to this subject. Remote sensing, people with experience in remote sensing is required every year more, because now we are moving towards spatial aspect with respect to all science. So this is a technology, this is a science, this is an arts. It's going to be used not only for geology, it is going to be used for almost all the subject to my knowledge. So understanding remote sensing is very important nowadays. So people have started in the foreign countries, they have introduced this subject even in the play school, right from schooling, right from first standard onwards, of giving how satellites is orbiting, how technology is being used. Now let us see one by one with respect to an introduction is concerned. So I would like to discuss the present lecture in the 8 different modes, by defining what is remote sensing, by tracing the history of its origin of remote sensing, explaining about the types of aerial photograph which is normally being started. Of course, still we normally here I am practicing by giving for my aerial photograph and its interpretation, as well as the satellite data visual interpretation. Once if you are very familiar with the visual interpretation, it will be easy for us to take up in the digital image processing and photogrammetry. And what is parallax, how that this is going to be linked with scaling the photograph, how human vision plays to look up from the satellite points of view, and to conclude the lecture. Coming to the definition, if you want to simply define that, that I don't want to normally take defining in huge length. Normally one should understand how this is there without physical touch or contact with any object is called as remote sensing. If I interpret, look at any object without touching the object, if I am telling, suppose if I am looking the monitor, I am just finding out that this is a red color, this is remote sensing. So it was given by 1976 by Linz and Simonet. So this is, I feel that this of course many of them have defined remote sensing in different forms. What I feel that one should understand, so this is the technology without physical touch or in contact with object. And the other Curtis in 1982, he also defined that some distance away, if you do what sort of interpretation about the object without touching, the same observation of the target by a device some distance away, you keep your distance away, that is remote sensing. And again Curran in 1895, he has actually the use of electromagnetic radiation sensors to record images by using, this is actually exactly satellite data what it does. He has explained the definition of remote sensing to more specific, the use of electromagnetic radiation sensors to record images of the environment which can be interpreted to yield useful information. So this is 1985. Of course, many of them of their own they interpreted to define what is remote sensing, but it is known to everyone that what is remote sensing without physical contact with the object. And this is how it is there. One small animation I have taken, you just see that how satellite is revolving on the earth without physical contact with the earth, and it takes information continuously. You have a strip of information, you can see here how it is moving, and it takes a strip of information continuously. So this is what you call it as without physical touch with the object. And again Harris in 1987 described the remote sensing in a different way, that by using different band, visible and microwave, infrared and other bands. So if you want to concise the definition of remote sensing, the main characteristics, it is nothing but physical separation between the sensor and target. Here you don't have contact, you have a medium to connect both. Satellite to Earth is your electromagnetic radiation, that is the energy given by the sun, that is called sonar, is an exception. So without, that normally we say that the backbone of the remote sensing is sun. Without sun you cannot imagine that you will not get energy. Once you are not getting any energy, you cannot get anything, reflection or radiation or emission or transmission, nothing. No, this science would have not exist. So device to sample or measure radiation is called a sensor. So sensor normally we are using in the satellite. So this electromagnetic radiation is captured by the sensor. Target is your surface of the earth. Sometimes you will be able to work with atmosphere to understand the different characteristics of atmospheric science, or you can also work with oceans to understand oceanography or land surface for various scientific studies. So this is the exact technology that how we are using. So you have Earth, global Earth is there. So this is the equator. You have satellites revolving. There are two types of satellites, of course, that we will see later. Normally it revolves 900 kilometers. Of course, they have given the figure that 350 kilometers. Some TRMM and other satellites which was kept here. Normally, the sun synchronous satellite, revolving north south around 900 kilometers from the ground. So this is the physical separation between the sensor and target. So sensor is kept here, target is here, no touch, physical touch with the object, but we do lot of interpretation now. Mainly science depends on remote sensing satellite data. So this is the electromagnetic spectrum, a very simple view of electromagnetic spectrum. Without this, this science would not exist. And again, this we will see in a detailed way that how different energy is there. And you see that this is the short wavelength, the distance between the two crusts increases longer wavelength. So shorter wavelength to longer wavelength, the red goes, and then similarly low frequency from here, if the wavelength is more, frequency is less, frequency is more if the wavelength is less. So this is the characteristics of the energy. That is also required for one remote sensing scientist to understand. Without understanding the energy characteristics, one cannot apply their knowledge, very excel in the field of remote sensing. So medium electromagnetic radiation for the sonar is an exception. And this is the device, radiation device called sensor. Just to look at that, this is going to be used for capturing the information from the earth by reflected energy given by the sun. And this is the ideal situation. Target is here, your sun is here, sun is giving energy, it travels and then hit over here, and then you have your device to keep and then take all this information. So you have varieties of information, you have varieties of sphere characteristics, you have varieties of objects over the surface of the earth. Either the land or the oceans can be captured. So target is terrestrial environment, like as I already told, atmosphere plays a major role, different spheres are there. Ocean, again, it is ocean science excellently they are using this technology, and land surface. So that is about the definitions of remote sensing. Now let us move to the origin of remote sensing. That is the second part of our discussion. The origin of remote sensing began with aerial photography. Normally people used to tell that that initially they have used birds to take up photograph, and slowly aerial photography came. Previous know that in 16th 17th century people have used only bird. They have used bird for taking photograph. This is the first photograph of a scientist taken in the year 1839. You see a fellow, the photographer is here, and this is the first photograph. It's that nearly 2 decades, more than 2 decades, 2.5 decades, 200 decades, 1839 to 2019. And origin of remote sensing, as I already told you, that initially they have used bird. Subsequently, in the second era, they have used balloon. A fellow who is standing over here and then looking by using the camera. This is the camera. In 1858, he is a scientist, Gaspar Flux Tournacon. He has used Nadar takes photograph of village Petit in France by using a balloon. So that's how the science have developed. This is the photograph of the scientists. You look at the photograph, very beautiful photograph, and they have started slowly understanding how the terrain is being used and what is their future plan to be done by using this type of photograph. This is another photograph, Boston by Black King in 1860. It is a Boston city. You can see that how the Boston city in 1860 by using balloon photograph. And you see, slowly they have used this technology during war period. So that is the another development we forced us to look at from the scientific point of view, how this technology scientifically can be evolved. So this is at World War One, the major impulse to develop aerial photograph, looking from the aircraft, and he takes photograph, and then subsequently they used for fighting with the enemies. After the war, the technology was in place to begin large scale aerial service. Yes. So you see, they have kept a separate flight for photograph to for scientific studies over the terrain. They have started utilizing this technology. So that is a lookup of origin of remote sensing. Coming to the next part of the discussion is types of aerial photograph. You know that aerial photograph scientifically divided into three parts that we will discuss one by one in the next. So this is one aerial photograph, a view of aerial photograph. Of course, it is a movie, it's not running. It is a movie, it's not running. You see, it takes photograph continuously. Once if it takes photograph, the color of the terrain and the color of the photograph is changed with respect to the characteristics of the land. So in flight is this is the flight is moving this direction, and it takes photograph continuously. So this is the direction of movement. It's a GIF image, it's not working. And it is divided into three types. One is vertical photograph, second one is low oblique photograph, and third one is high oblique photograph. So vertical photograph is a photograph taken straight away from the lens. You know that this is vertical. It means it is equal in direction, equal in distance, both at left and right. You see, your photograph is not distorted. Once if you use vertical photo, normally scientifically, if you want to work with respect to scale of the area, that you will have to depend only on vertical photograph. Low oblique or high oblique will not be, the scale will not be uniform everywhere. So this is vertical. It means from the lens to the ground, if you connect a line, it will be very straight. That is vertical. And low oblique, it means, you know, that from the lens center it is slightly getting away. You see that this portion is very closer to the lens, and this portion is very far away from the lens. So this is a sample photograph taken like this. What will happen? So this is low oblique photograph. Once if low oblique photograph will be sometimes required to have a synaptic view of the terrain. But normally speaking, scale distortions will be there with respect to this photograph. Scale distance, you know, here it's very high scale distance, here it is very less, because and if it is 1 centimeter may cover half kilometer, here 1 centimeter may cover 2 kilometers. So that's the difference if you use low oblique or high oblique photograph. So this is another very interesting high oblique photograph. Normally we say that one end of the photograph touches on the ground, the other one of the end of the photograph touches on the sky. You see, even this is a sample of the photograph. One end is there with respect to touching the earth, and the other end you see the sky is connected. So this is high oblique. It means, you know, that angle of photograph is so high. Again the scale problems will come. But normally if you want to map where flood is there, where any disaster, by the time you don't need to look at with respect to scale. You need to know what is the condition of the terrain, or to map the disaster zone, you can use this type of photograph. So there are three types: vertical, low oblique, and high oblique. High oblique, you have to keep it in mind that at one angle falls, the other angle of the photograph is very high, it touches on the sky. So that's the explanation of the high oblique photograph. So vertical is most important as it is minimum distortion. As I first initially told, this is the vertical exposure, this is the lens, this is the exposure place where you keep your film. Here it is exposed about the terrain characteristics. So there are four ABCD. Frame is there, film positive, and this is the haptic axis. Haptic axis will be, as I said, it's straight perpendicular to the ground. So this is the distance of HH, this is the distance of focal length from the exposure to the film, that is focal length. HH is the total flight height. So you will be able to easily interpret the photo scale of the aerial photograph. And normally one should know how aerial photograph has to be studied, that every film they have kept a V-shaped notch on all the sides, all the four sides of the center, that is called fiducial marks. Very, very important one. So what it says that it is a film, if you connect fiducial marks exactly at the center, you have to have a principal point, then only it is a vertical photograph. So here what does it mean? Here everywhere the scale is uniform. If you map and then take it to any environment, you will be able to interpret with respect to spatial concept of the terrain. And if you connect, as I said, this fiducial marks on both sides, left to right and top to bottom is connected, and this is the center point at which you have your principal point. Principal point is occurs at here. So this is principal point, and you have marginal information. When the photograph was taken, what is the photo number, everything. If the flight moves, you need to have all the things to arrange your photograph. Everything it is there here to understand types of aerial photograph. And scientifically they have moved that they wanted to use this technology. They need to have a terrain status continuous, and they want to map it with respect to spatial concept is concerned. So scientific way people have started taking this information. You see that an aerial photograph mission will flown by strips. You see this is the movement. Normally what will happen, that flight will start, it will move like this. This is called flight planning. It will move. Already they will set the path, and then parallelly this will move. This is the direction of the movement. Once if it moves, this is the direction of movement. You need to have overlap, you need to have side lap. There are two things are there. So this photograph will have 60% overlap. Once, why you are going for overlapping? So that you can generate 3D information, not only with the 2D information. You also need to have side lap to have to cover the whole area. That is that they have given shutter timing set for 60% overlap, and the strip speed is set to 30% side lap. So this is very important. Slowly we have still for large scale mapping, even though we have a big satellite like digital globe, but still aerial remote sensing plays a major role with respect to military is concerned. And end lap, that is called forelap. People say overlap, end lap, forelap. All the words are same, equal meaning. Is an important bit, 60%, as I said. It ensures every point on the ground appears in the at least minimum two photographs. One is at front, one is at back. So only first photograph will not have back side of it, but all the photograph will have continuous stripping of 60%. That is called the overlap, end lap. Distance between principal point of the adjacent photograph. You know that if you have principal point, as I have already told you, if you connect fiducial mark, the center point is called as principal point. So one photograph will have one principal point, the second photograph will have second principal point, but overlap is 60%. The distance between PP and the PP of second photograph is called distance of airbase, distance of flight. So that is called the airbase. This is also a very important word for us to understand. So this is a very small introduction. Of course, it is not being much used by many scientists, but anyway, we have to trace what is the history. Sometimes that the old will help us to understand very clearly what we are doing in future. Coming to the next part of the discussion is photogrammetry. It is nothing but grammetry comes mathematics in the photograph. Right, mathematics in the photograph, you see, if you know, as I have already told you, if you know the focal length of the camera, the focal length always in the camera it is being given, and the height of the flight which you have kept and then taken photograph, you will be able to understand the photo scale. So this is the photo scale. Photo scale is always represented by the formula called f by h minus h. What is h minus h? H minus h, you know what is f, focal length. It is the distance between the camera film to the lens. The total height is the flying height. Normally total height is represented by sea level, but you know that if your ground terrain is height, so this is the area you are going to capture. You will have to minus this, then only your scale will be correct. So the total h is reduced from the height of the ground from mean sea level is h minus h. So if you know the focal length, if you know the flight height minus above mean sea level, h, capital H minus small h, you will be able to predict what is the scale of the photography. If you know the scale of the photography, once if you know the scale of the aerial photograph, 1 centimeter represents how many kilometers on the ground, how many meters on the ground, how many inches on the ground. So this helps us to understand again for detailed mapping on the surface of the earth. So this is another very interesting, as I already told you, once if you know the scale, you will be able to draw any area. This is one classical examples how that this map is going to be. Once if I am drawing, I will be able to know what is the place, what is the area of this. If I know what is the area of this, if I know the, what they are doing inside, then I can be able to predict well, and I can be able to project also this is called 2D measurements. Only you can do 2D, not with 3D. 3D is also possible by using 60% overlap and 30% side lab data. So it's nothing but horizontal. Photogrammetry will gives you measurement in terms of 2D if you use only one photograph without any merging of left and right eye. You'll be getting 2D information. Now you'll be getting 3D also by true measurements. If you take two photographs and you'll be able to get the height of the terrain. You see what is the height of the terrain around 16 meter, what is the length of the terrain is 16 meter, what is the depth of the terrain, everything. So there are a lot of other softwares helping us even to map. If you take up left photograph and right photograph and fuse together, once if you fuse together, what will happen? You will be able to get all the height details. So 3D you can generate through aerial photograph. Coming to understand what is parallax, it means normally this plays a major role. By using a parallax, you will be able to understand the distance. You see, you have a object, two objects. So this is right eye. From right eye you are looking, from left eye you are looking, and two objects are there. One is pencil, the another one is a building. A pencil is looking near to you because the object is very nearer to you. That's why it's big and its height. The object is very far away from you. That pencil is displaced because it's very near to you and it is far away. Parallax represents the distance of the object from the left eye to right eye. It will vary from person to person. You see, this is a very classical animation once you can understand. And there is a movement, you see that once if this comes, this object is very nearer, and if red comes, red is very nearer. When this object comes, by the time the other ball is far away. When this object comes, again you see, now you will understand. If I am looking at from here, this object is close. If I am looking at from here, wherever you are looking, your left eye and right eye, where it coincides, this is called as the shifting of the distance from the look, from the direction of look is called as a parallax. So this is very, very important for you to understand that parallax concept. Normally parallax being, that from the eye you can have a star. What star is very nearer to you, you will be able to understand. Distance will give you by using a parallax bar. By using a parallax bar, you can have, so how this is going to be used for this remote sensing technology, you can see this is a right eye photograph, this is a left eye photograph. Once if you fuse, you will be able to get the height of the building. Once if you get the height of the building, so this plays a major role for understanding the 3D concept of aerial photography. So the height of the object can be taken by using this formula, height of the aircraft and absolute parallax difference being measured of the height of the building, and what is the difference of the height of the building with respect to the height, the total height, will be able to get it by using a parallax. And we'll move to the human vision, how human vision plays a major role for photogrammetry, for types of photograph, for aerial photo interpretation, and sometimes 3D satellite images also. You have two, eye angle, the two eye angle fuses together. This is the minimum distance of fusing, and this is the maximum distance of fusing. So exactly if you want to tell, this is the fixing point at which you will be able to get very comfortable, and the distance between this is called as the pupillary distance, interpupillary distance. It will vary from 6.5 to 7.5, 6 to 8. Normally people know it's the distance between the two black eyes. So it will vary, and based on that you will be able to get the depth of the object. So this is one small instrument called lens, a pocket lens, or similar type of mirror stereoscopes are there. You can have your look, that from left angle, this is the angle of area, look up. From right angle, this is the angle of area, look up. Of course, I am reverse by explaining. This is left to a person, this is right to a person who is looking from that direction. And once if it is fusing both together here, so this area, we will get the 3D stereoscopic viewing of the Earth's surface. It is possible by using satellite data. So to conclude, we have seen what is remote sensing, how the definition goes, and then how the technology was started with respect to origin, and in terms of different types of aerial photography, and what is the 2D and 3D differences, and what is the role of human vision in binocular and taking it up from 2D to 3D. That's all about a very small introduction about the remote sensing. Thank you.